Morning, everyone. I'd like to welcome everybody to our PARC seminar today. Also like to welcome all the members of PARC who may be joining us online, and in particular the PARC grad student and postdoc group who will be joining us. So today our speaker is Dr. Jennifer Ogilvie, who's an assistant professor of physics and biophysics at the University of Michigan. Jennifer is a native of Canada and got her degrees in Canada and most recently her PhD from the University of Toronto, and then came to University of Michigan, where she studies the dynamics of biological systems over a wide range of time and length scales using nonlinear spectroscopy and microscopy. So she's going to tell us about the work that they have been doing in Photosystem II using two-dimensional electronic spectroscopy. She also does single molecule microscopy, spectroscopy, to look at dynamics that might be hidden in ensemble measurements, so you can see it in a single molecule system. So, Jennifer, thank you for coming, and forward to hearing your talk.
Well, thanks so much. I think we have two mics going there. Sorry. How's that for volume? Is that pretty good? Yeah? Okay, lights. Maybe a little bit. Okay. Great. Well, anyway, thanks so much for the invitation. It's great to be here. So today I'm going to tell you a bit about the work that we're doing in my lab, focusing on our work to try to understand the Photosystem II Reaction Center. So I think for this audience, I don't need to do much of an introduction about Photosystem II. So as a spectroscopist, we need to simplify the system. And so rather than looking at the full multi-protein complex, an extremely important system. Of particular interest, of course, is its ability to do water splitting. So today I'm going to be talking about our work looking at the D1, D2 isolated reaction center in a moment. That'll show up here. So we'd love also to look at the other proteins involved in Photosystem II's function, but we're beginning with the reaction center here. That's what I'll be talking about today. So we, in fact, study a simplified preparation that is the D1, D2 cytochrome B559 complex. And our reason for doing so will become clear as I talk a bit about the spectroscopy that we use. So we want a system with a well-defined structure that has a relatively few number of pigments. And so, so this simplified reaction center is about as simple as one can get, but still performs some of the interesting charge separation processes in the Photosystem II Reaction Center. So in this system, it doesn't do the full charge separation, electron transfer processes, or water splitting, but it does indeed perform this initial charge separation that's important for the function of the PS2 Reaction Center. So this system has been studied by a huge range of spectroscopic methods, and really the challenges here are the fact that all of these pigments, all of these 6 chlorophyll and 2 theophytin absorb in the same frequency range here, contributing to this broad QY transition. And so there have been a wealth of transient absorption, hole burning, many other spectroscopic studies of the system. And what we'd like to really understand is the underlying structure of this QY transition. So the challenges facing the spectroscopist are, as I mentioned, overlapping absorptions. Also the fact that there are both energy transfer and charge separation processes happening in the same similar timescales in this system. And so despite the wealth of work that's been done on the system, there are still questions about the underlying design principles, we want to understand the structure-function relationship in this system. How does one describe the electronic coupling? And what are the pathways of charge transfer and energy transfer? So I'm going to talk briefly about the method that we use. I think for some of you this will be elementary, but hopefully it'll be instructive for those of you who don't do ultrafast spectroscopy. So if I want to look at energy transfer between a donor and an acceptor pair, then using pump probe spectroscopy, we could do this the following way, where if we choose a frequency that will excite our donor, and then wait some time for the energy to transfer to our acceptor, and then bring in a second pulse after that time delay, and probe the emission from the acceptor, then we get a clear signature of energy transfer happening. Now, things get, in some cases when you have well-separated transitions between donor and acceptor, this can be very easy to see energy transfer. However, when you have many overlapping transitions, one needs to use broad bandwidth pulses, and you lose the ability to selectively excite a particular pigment and know that that's what you've excited. And so in trying to improve time resolution, having to use broadband pulses, ultimately we lose information about excitation frequency. So one way around that is to add a dimension to the spectroscopy. So some of you may have read this book. It's a nice illustration of how adding a dimension can give you new insight into things. So in this book, of course, the protagonist lives in a world of 2 dimensions, and a lot of the characters he encounters daily look the same to him. But one day he's visited by an alien who brings him into a 3rd dimension, and he gets to see that having that extra dimension, many of the characters that he thought looked quite similar are actually different. So how do we do that in our spectroscopy? Well, we do that by adding another laser pulse. And so rather than having a 2-pulse sequence, we have a sequence of 3 pulses. And that means we have 3 time delays. And we record our signal is radiated due to this 3rd order polarization created from the interaction of 3 laser pulses with the sample. So this is basically the optical analog of the simplest 2D NMR experiment. What we're going to do is Fourier transform with respect to our first time variable to get an excitation axis, and then Fourier transform with respect to our 3rd time variable to get a detection frequency axis. And we'll get one of these 2D spectra for each waiting time here. So just, I want to highlight some of the things about this spectroscopy that make it useful for studying photosynthetic systems, like the PS2 Reaction Center. So if I have a really simple, just 2-level system, the 2D spectrum is very boring. So in this case, I would excite at a given frequency and detect at a given frequency. And this diagram here just shows one particular process that can give us a signal. There are other processes that contribute as well. But things get more interesting if I have an inhomogeneously broadened system. So here, perhaps, for example, I have many pigments that are in different protein environments, and the protein environment tunes the resonance frequency of their electronic transitions. Now in my 2D spectrum, environment that changes in time, and when it changes, it may alter the resonance frequency. And so we can see this in the 2D spectrum by varying this waiting time. And basically, if this subpopulation of pigments that absorbed over here undergoes dynamical fluctuations that change their frequency, I can I can see that happening by watching the shape of the 2D spectrum change in time. So I can get an idea of the length scale, or the time scale in which spectral diffusion processes occur, and then I can also look at static disorder very nicely as well. So if the system never rounds out and becomes symmetric, then that tells me that I have some degree of static disorder left in the system. So I can measure both static and dynamic disorder this way. It's also very useful for looking at electronic coupling. So, for example, if I have two pigments that are weakly coupled, so perhaps they might undergo Forster energy transfer, then my 2D spectrum will look something like this, where I would have transitions along the diagonal that are elongated if they're inhomogeneously broadened, but no cross peaks. Whereas when I have stronger coupling, now when I include coupling and diagonalize the Hamiltonian of the system, I get shared excitations, or so-called excitonic states. In this case, I have a common ground state, and that leads to these cross-peak features of the 2D spectrum. So by looking at the cross-peaks, I can learn about coupling, and then I can also, in the weak coupling limit here, I can look at energy transfer as well, and the strong coupling limit for that matter. So looking at the dynamics of the cross-peaks tell me about how energy is being transferred between different excitonic states. So just to summarize, so the method basically gives a nice trade-off between maintaining high time resolution, but also providing information about the excitation frequency. So compared to a pump probe experiment, basically we get this additional frequency axis here. If you integrate along that axis, that produces the information in a pump probe experiment. And so signals that are located in the cross peaks, things like electronic coupling and energy transfer, can be nicely separated with this type of spectroscopy. Okay, so this method has been around for a number of years now, but some of the experimental challenges that that prevented it from being done earlier. So even Ernst, in the early days of NMR, knew that it would be interesting to apply the methods at other frequencies, but doing so at visible frequencies has some particular challenges associated with it. So in particular, because the frequencies are so high, in order to get the maximum information from this type of spectroscopy, one of the main challenges is needing to have extremely high timing accuracy of the time delays. So because this is a Fourier transform method, we get our frequency axes having measured time delays. And so you need to have extremely high accuracy in order to get reliable frequency axes. Also, in order to get both phase and amplitude information in these types of measurements, this can tell you interesting things like the sign of different signals and help you understand the origin of different parts of the 2D spectrum. You need to do interferometric measurements, and that requires high phase stability. And so as a graduate student, I worked on this in Dwayne Miller's group, and we came up with a scheme for doing this, very similar to the scheme that Graham Fleming also uses in his lab, and now a number of other groups as well. And so that sort of development led to the first work on using this type of approach on a photosynthetic system by Graham Fleming's group in 2005, where they looked at the FMO complex. Of course, there's been a lot of exciting work since then, inspired by this first work. So in my lab, we're using sort of a different approach for doing 2D spectroscopy. So you just think about a laser pulse. So if I want to represent that mathematically, I have a spectral amplitude and a spectral phase. And the spectral phase is critical for determining how short your laser pulse is. So if I have a flat spectral phase for a given amplitude, that will give me the shortest possible pulse. However, rather than just having a flat spectral phase, it's also possible to manipulate the spectral phase using pulse shaping technology. So one way that there are a number of different ways to shape a laser pulse, but a simple way is to take a grating and spectrally disperse your pulse. And then when you've got all the different colors separated here at the Fourier plane, we place a pulse shaper. And this has many different This is a liquid crystal display with 640 pixels. A applying different voltages to these allows you to adjust the spectral phase. And then you put the pulse back together again. And with such a device, this is very useful for 2D spectroscopy because one can mimic an interferometer. So you can put one pulse in and get two pulses out at a time delay of your choosing within limits. But for the spectroscopy that we do, we can generate the time delays we need. It's also possible to control the relative phase of the pulses that allows you to do some interesting things in the spectroscopy. So this really ends up making it's not too echoey, making the method quite easy to implement, as you'll see in a moment. So we've been using very simplified geometry for doing this type of 3-pulse experiment. So in our geometry, we have 2 pulses that are collinear, and they're derived from a pulse shaper. And then we have a 3rd pulse that comes in at a small angle. And so some benefits of this, I'm not going to really get into the details here, but other methods of 2D electronic spectroscopy require that you record 2 different signals. In this case, they come out in the same direction, and we can readily collect them without worrying about timing errors. So it's quite a simple way to do this. We also automatically do an interferometric detection method. So the experiment looks something like this, where we have an amplified titanium sapphire laser and 2 home-built non-collinear optical parametric amplifiers to give us tunable visible light for the experiments. One of those we send into the dazzler to create the first pair of pulses, and then the second pulse, or the 3rd pulse rather, is derived either from a second NOPA, or from focusing tightly into a sapphire plate to generate a white light continuum. And then we cross our beams at the sample and record the signal in a spectrometer. So this type of method, doing 2D spectroscopy with a pulse shaper, was first done by Martin Zandi's group in the infrared, and then we followed closely after doing this in the visible. And so, any groups doing 2D pump probe spectroscopy can easily do 2D by adding a pulse shaper. And what's nice about this particular arrangement is that you can incorporate this continuum probe very easily. So what that does is, typically in a 1-color 2D electronic experiment, you get access to a relatively small region of the 2D frequency space. With a continuum probe, one can expand that considerably and look at energy transfer between quite different electronic transitions with relative ease. So I'm going to talk just briefly about some of the things that we've done initially in order to understand what affects the line shapes in 2D spectra. So we know that there's a lot of rich information in 2D spectroscopy that can tell us about electronic coupling and dynamics. But we also know that we need to make sure that we understand all of the possible effects that can be confounding in this type of spectroscopy. So one of the first things that we did was to think about what would happen in a system where you've got strong vibrational wave packet dynamics. And so we picked a system that had been looked at with other 3rd-order spectroscopies where the vibrational wave packets had been observed. And so this Perry system was a good one to choose here. So here the black is showing the absorption spectrum of Perry. This is a vibronic progression of a 1400 wave number mode. And in this system, a number of groups, Fleming's group in particular, had seen a very strong 139 wave number mode modulating the 3rd-order response. And so in our pump probe data, we do indeed see that. And then in the 2D spectra, we also see modulations at this 139 wave number mode. And we see modulations of all 3 of the peaks here. So here we're doing this continuum probe 2D spectrum. So that's why we've got such a broad detection frequency axis compared to our excitation frequency axis. So if you'll notice here, the ellipticity of these line shapes is changing in time. You might have to, and as well as the amplitude changing in time. And it's doing so at the period of this 139 wave number mode. If we plot the data, we see these modulations here. And so, so the point here is that vibrational wave packet dynamics do modulate 2D peak shapes. So one needs to make sure to take that into account when modeling these types of systems. A lot of the pigments have low frequency modes that will contribute to the 2D spectrum. When short laser pulses are used, it's possible to impulsively excite these vibrational modes. So this is just a simulation of Perry showing that we see this type of modulation of both the line shape and the amplitude in all three of the peaks. Also, so with this type of pulse shaping setup, it's easy enough to look at what happens when your pulses aren't perfect. And so here we chirped our probe to look and see what happens. It's easy to think about what that means in terms of the 2D spectrum. When you chirp your probe, basically you have a frequency-dependent time delay for this second time interval here. And that leads to these types of distorted spectra here that we were able to simulate reasonably well. And so my point here is just that yes, there's a lot of information in the 2D spectra, but you also have to be extremely careful with taking everything into account when you're interpreting the line shapes. So with a pulse shaper, as I mentioned, it's easy to adapt a pump probe experiment to do 2D, and automatically provides the absorptive spectrum. I didn't really talk about what that means, but here, this is the sort of highest resolution 2D spectrum one can get. And then here I've already discussed that. So on to the application to the Photosystem II Reaction Center. So here I'm going to show you a movie of our data taken at 77 Kelvin of the 2D spectra of the reaction center. So this first spectrum, very close to time zero, you'll see this elongation here. This is due to the fact that we've got inhomogeneous broadening in the system, a lot of static disorder. You'll also see cross peaks here present even at this early time, indicating exotonic coupling in the system. So now I'm going to play the movie, and what you're going to see mainly is the transfer of energy from the higher lying states down to lower energy states. So you're going to see the growth of this cross peak here in time. Okay, and so we'll scan out to about 200 picoseconds. And so you probably noticed that most of the relaxation, most of the changes in the 2D spectrum actually happen within the first couple hundred femtoseconds. That's when a lot of the relaxation occurs. Let's cycle it one more time. Yeah. Okay, so even by a couple hundred femtoseconds, this cross peak has grown in considerably. So there's a lot of rich kinetic information in a 2D spectrum. So we've been thinking about how best to extract that information. So one approach that we've taken, also in order to make connections to the transient absorption, the many transient absorption studies done on this system, is to basically take each point in the 2D spectrum, and what had been done in transient absorption data was to do a 4 exponential fit. So here we're going to do that to every point in the 2D spectrum. And then what we're interested in is seeing what parts of this 2D spectrum change on similar timescales. And we'd like to be able to use those to understand, or hopefully to tie that to actual intermediates that undergo different kinetic processes. So what we do is we sort the lifetimes and associate them into 2D decay-associated spectra. So this is very similar to what's often done in transient absorption, where you are looking for spectral signatures of intermediates. So basically what we do is we look at what's occurring within the fastest time window, sort of intermediate times, grouping into a total of four different intervals, and then looking to see what parts of the spectrum contribute to kinetics on those time scales. So here's the fastest time scale. So anything that happens faster than 400 femtoseconds is represented amplitude map here. So this is saying how much the spectrum is changing in these different frequency regions. So the negative here corresponds to growth, while the positive corresponds to loss. And so here you're seeing a lot of loss from the higher energy states as they transfer energy to this to the lower energy state here. And then here's the corresponding lifetime map that shows for each amplitude point what the corresponding lifetime of that kinetic process was. And so this lifetime distribution here shows sort of just, this is just a histogram of all of the different lifetimes, an amplitude weighted histogram of the lifetimes present in, within this fastest component. So we're seeing a lot of relaxation on this 100 femtosecond time scale. Okay. Then looking at longer time scales, so in the 1 to 3 picosecond range, we see the largest changes in amplitude down in this lower energy part of the spectrum, and with the lifetimes shown here. And the lifetime distribution is spread sort of between 1 to 3 picoseconds. So transient absorption studies done using selective excitation, so narrowband excitation by the Van Grondele group, have proposed the existence of 2 different charge separation pathways. So in this pathway here, we have the pheophytin and accessory chlorophyll initially involved in the charge separation, leading to the final charge separation here. Whereas there's a secondary pathway initially starting at the so-called special pair with the accessory chlorophyll on the D1 side, leading to initial charge separation prior to the secondary electron transfer step. So the timescales here are 3 picoseconds to 1 picosecond. So our data is consistent with that. If you recall this histogram here, we're seeing certainly kinetics that span that range of timescales. You'll also notice these other sort of 40 to 60 picosecond processes. So looking, whoops, yeah. Yeah, so as I mentioned, consistent with that. We also see sort of this elongation that can tell us about static disorder in the system. So looking longer at the third component, kinetic component, so this is in the range of 5 to 80 picoseconds. So we see sort of a distribution of lifetimes out here. Again, consistent with the transient absorption studies. And that we also saw a faster process that has been interpreted by some as lower energy transfer from the peripheral chlorophylls. Okay, so this final component here, we can't say much about it. Our current setup only scans out to 200 picoseconds, so we in fact fixed this time scale based on transient absorption measurements to 2 nanoseconds, so that because we couldn't legitimately fit anything on the nanosecond time scale with our measurement. But the spectral feature tells us sort of what the charge separated state looks like. So we'd like to be able to say something about this 2-pathway hypothesis. And so one thing we've done recently is to chemically reduce the reaction centers to try to block this one of the 2 pathways. And so when we do that, we do see results that are consistent with this blocking of one of the pathways. So if you recall, so this pathway was thought to be slightly slower than this pathway here, so 3 picoseconds versus 1 picosecond. So here I'm showing, this is the regular unreduced reaction center data, and this is the reduced reaction center data. And you see from the lifetime histograms that we do see a shift where most of the amplitude is closer to 1 picosecond, which is consistent blocking this chlorophyll D1 pathway. Okay, we also see quite a few differences in the spectra. This is something we're working on modeling to better understand. Also, in the secondary charge separation step, we see some differences here too. So you'll see, I apologize, I realized I didn't plot these on the same time axes, but you can see that, that there's definitely a shift to the faster timescales in the reduced data. Okay, so what else are we doing to understand the system now that we've got the 2D spectroscopy measurements on it? So what we've been doing is taking excitonic models in the literature and using those to simulate what 2D spectra would look like should those models be correct. So this is a model from the Van Grondele group, and I'll describe it in more detail in a few moments. But the basics of the model are, so here, here's the here are the pigments involved, and the colors correspond to, so they have 9 different excitonic states in this model. So the colors are basically telling you which pigments participate in which of the different excitonic states. And they've also, in this model, introduced a single charge transfer state. This charge transfer state was postulated based on Stark spectroscopy measurements that they made. So how does one take such a model and get 2D spectra from it? So basically, the model begins with having some idea of what the site energies are and a good crystal structure from which you can calculate electronic coupling. In this case, they used a simple dipole approximation for calculating the coupling, and we did the same thing. That gives you the system eigenstates, and then, of course, you need a description of the bath. So this is the protein, so we need to put in the important, or somehow parameterize the bath and how it's going to interact with the system. From that, one constructs a 3D response function and can simulate 2D electronic spectra. So here's a little bit more details of the model. So we took their model but updated it a little bit using the newer higher resolution crystal structure that came out last May. And so these are the exciton transitions that we get within this model. And the spectral density that they use to describe the bath in their model consists of basically an overdamped Brownian oscillator, along with a number of underdamped vibrational modes that they derive from fluorescence line narrowing experiments. So this is taken straight from their modeling. And so this is sort of this is how it comes out when you put those things into the model. So here's data on the left for 2 different waiting times. This is 200 femtoseconds and much later in time. So this is the Novotoreshkin Van Grondele model at those same times. So you can see that some of the features of the 2D spectrum do match. The diagonal elongation and the relative width of the diagonal to anti-diagonal look quite good. There's a presence of a cross peak here at early times. Other features clearly don't match very well. So we have taken their model and modified it, basically played with the parameters that were easy to play with, and we can get slightly better agreement with this cross peak feature by increasing substantially the system bath coupling. In doing so, we needed to decrease the amount of disorder in the system to maintain reasonable agreement with the linear spectroscopy. But you can see that, so we get this cross peak better, but the anti-diagonal width is too large. So we've had to decrease the static disorder too much in order to try to reproduce this feature. But I think, more significantly, the kinetics are clearly not right at all in this description. So this amplitude reduction in the data is huge over this 100 picosecond time scale. While in the model, we're not reproducing that at all. So just to summarize some of the observations that we have from this first study on the PS2 Reaction Center, so we did see obvious cross peaks at early times, indicating excitonic coupling as was thought. We also had high time resolution measurements of the energy equilibration, and the kinetics that we've observed do seem consistent with this two-pathway model, and we've been able to test the current excitonic model. So, obviously there are a number of remaining challenges. So the model, I didn't really get into the details of how it describes the relaxation processes, but so this model uses modified Redfield theory, and this has been shown to work for a number of different photosynthetic systems, but seems not to work very well for the reaction center. Part of the problem here, in general in these systems, there's a wide range of electronic coupling, even within a single complex, and also system bath coupling as well. And so one thing that's been done by the Van Grondele group is to basically use different relaxation theories to treat different parts of the complex, and tailor the theory to be able to describe energy transfer between different pairs within the reaction center. So they've been able to model some of their recent pump probe data quite nicely using this compartmentalized approach that uses modified Redfield for part of it, or generalized Forster theory for other parts. What they haven't shown is the full picture with pump probe as well as all of the linear spectroscopies. What we've found is that it's very tricky to get everything to match. So you want, of course, to maintain good agreement with many different linear spectroscopic measurements, but also get good agreement with the 2D spectra. And what we found was that when we adjusted parameters to improve agreement with the 2D spectra, that was at the detriment to agreement with other measurements. So so that tells us we still have quite a bit of work to do in modifying these models. In particular, this model that we tested didn't really have any sort of true description of the charge separation process. They had included one charge transfer state, and that's it. And then, so we believe strongly that one needs to incorporate the charge separation explicitly. And so Shaul Mukamel and former postdoc Darius Abramovicius have recently published a model for doing this, and we're working with them on seeing what kind of 2D spectra it predicts. We hope that it may even be able to give us insight into this 1 versus 2 pathway transport model. We've also found in playing with the simulations that the 2D spectra that result are extremely sensitive to the spectral density that's used. And so we've recently been looking at using a model from Renger's group that seems to give slightly better agreement with the 2D spectra, but that's still under development. So as an experimentalist, all of this stuff is important, but we're not a theory group, so we're trying out models that other people put out there. But I think our main focus is on getting better measurements that can give good feedback for this important problem. So one of the things that we've done recently is to apply our continuum probe method. So previously I showed you data that was focused on the QY transition. And one of the big problems with it is that looking just at the QY, it's very difficult to say what spectral changes are due to charge separation and what ones are due to energy transfer. So we want nice, clean signatures of charge separation. And so with this continuum probe method, what we can do is excite across the QY band, but then probe broadly. So far we've looked out here at ion bands out near 460 nanometers. And so that will give us a better, a cleaner view of what the charge transfer processes are. Previously, we had to rely on assignments made by previous measurements for saying that the 1 to 3 picosecond range was due to charge separation. So here, the hope is that we can correlate the spectral changes we see here with excitation in the QI band, and really be able to better pick apart the charge separation processes. So this is some preliminary data. The QI data, initially we thought that was hard to get. That was nothing compared to getting these really weak signals down here. So here in this spectrum, this red, the QI data was the signal was so nice and bright there that we truncated it, so it looks a little weird. But that's just so that you can see these very weak bands. So this is the QX band, the pheophytin, and these ion bands down here. So this is still work in progress. We've been improving our signal to noise, and I think we can do substantially better than this, at which point we'll look at the kinetics of both the unreduced and reduced PS2 reaction centers. So another thing that we've been, just in the last few minutes, I'm going to tell you about another direction we've taken in trying to get other probes of charge transfer. So we were inspired by some nice work done by the Matthews group and also by Yoshizawa, applying stimulated Raman spectroscopy in order to learn about the vibrational structure of excited states. And so these groups have studied beta-carotene. Rich Matthews' group has studied a number of interesting biological systems, rhodopsin and GFP, using this method. So the idea here is that you're going to reach some excited state, and then on that excited state, use stimulated Raman spectroscopy to probe the vibrational structure. So some of the benefits, here you can do this on a dark state. It's also been shown to be sensitive to charge transfer in GFP and also in some other charge transfer systems. Okay, so typically this is done by using a so-called actinic pump to start the photochemistry, and then combining a a narrowband Raman pump brought in time with a short continuum probe. And the combination of these two basically do the stimulated Raman process. And by using a combination of a short pulse and a long pulse, one effectively time gates the signal and gets better time resolution than one would get with just a single, very long, temporally long Raman pump. So this is quite easy to do in the way we do 2D spectroscopy, if you recall. Here it's quite easy to modify the probe pulse to basically add something like a stimulated Raman probe. So previously, so the sort of standard femtosecond stimulated Raman or Fizzer's experiment is to use a single pump pulse and then do this stimulated Raman probe. Here, to turn this into a 2D measurement, we're going to use two pump pulses that are electronically resonant, put the time delay in between those, and then after a certain waiting time, have this stimulated Raman probe. Okay, so the frequency axes here are going to be obtained by this time delay here, and then by frequency resolving the Raman shift. So to the experiment, it's quite easy to add a single Raman pump. So we've upgraded to a higher power amplifier, and then we use some of that 800 nanometer light, spectrally filter it to get a picosecond Raman pump, and then just add that beam into the experiment. And so why would we be interested in doing this? I mean, the basic idea here is that under these broad line shapes, we hope to be able to obtain spectral signatures of different excited states. So if the excited state has a different vibrational structure from another excited state and from the ground state, then we can observe that with this type of spectroscopy. So here's just some some ground state data with our setup, so we can get very nice stimulated Raman spectra. The starred peaks here are due to we're looking first at rhodamine 6G because it's a nice simple system to work with. So all of these extra peaks are due to rhodamine. And here's with the actinic pump. So we've been able to detect new frequencies on the excited state with this setup. And then here's the 2D version. And so this is our first 2D Fizzers data. And we haven't yet applied it to Photosystem II, but we do know that the experiment works, and that here these lines here are basically the vibrational, or the Raman peaks that we observed you can see more clearly here in this 1D spectrum. And so the goal here is basically to learn about the vibrational structure of excited states. In particular, we're interested in looking at charge transfer states and hoping for some vibrational information about those. So ongoing work, as I mentioned, we've shown you some initial data on reduced Photosystem II reaction centers. We need to repeat those experiments. We're also very interested in looking at Photosystem II core samples. So we've so far just looked at the D1, D2 complexes. There has been some criticism that those may not be representative, that the charge separation may not be representative of what happens in PS2. There seem to be two camps on that. Haven't decided where I sit yet, but we do want to study the core samples and see whether we see substantially different 2D spectroscopy on those systems. That'll be challenging because of the many other pigments. So we'll be looking at the reaction center plus CP43 and 47. A very interesting system that Bob's been kind enough to give us some samples of Acaricularis marina. So of course this is a system that you guys no doubt know a lot more about than I do. But the idea of having a system with chlorophyll D is very appealing. In particular, it would be great if there's also some chlorophyll A in there. So this spectral congestion in the Photosystem II Reaction Center has really been one of the biggest impediments to understanding the spectroscopy of it. If we could have even one or two pigments that were shifted out of that 680 region, that would be fantastic. So we've been working with the samples that Bob has given us to try to get an equivalent D1, D2 prep. We haven't got it yet, but we're still working on it. And then, as I mentioned, we're interested in developing new spectroscopic probes of charge transfer. And in the meantime, working with theoreticians to get, to give them experimental feedback for their modeling efforts. So with that, I'd like to acknowledge my group. So Kristen and Jeff took most of the PS2 data that I showed you today. Frank is the next generation PS2 person with some help from Dan and Sechkin. And Charlie Yoakum has been a wonderful resource. He's been extremely patient with the students in my group, who are mainly physics students, teaching them everything from how to make a buffer to all of the more complicated stuff. And Shaul and Darius for the modeling, and DOE for the great support that they've been providing for this. And thank you for your attention.
Okay, we have time for a few questions.
So on your reduced reaction center experiments, did I understand correctly that you have one of the two pheophytins reduced?
Yeah.
And how do you do that? What's the conditions?
So the conditions, and I'll be happy to hear from you about this because I'd like your opinion about it. So here we've basically used sodium dicyanite and done a reduction that way. Is that?
Well, it's different than bacteria pheophytin, because I would not reduce the pheophytins. And you know, it's different. It's a different molecule. So I was curious. I don't know. I don't have an opinion because I don't know.
Yeah. So there have been some other people that have done this prior to us, and they've looked at you know, different spectra, reduced and unreduced, and think that that's a reasonable interpretation.
In the bacterial reaction centers, that's used to reduce the quinone.
Okay. Yeah, there's no quinone in our preparation here. But
Dewey's sitting there thinking that you have to do photoaccumulation in bacteria.
Yeah, that's.
So
I mean, that would be another.
I was just curious what the conditions are.
Right. Yeah. So we basically take a small amount of dithionite and do the reduction that way. We would like to do photo reduction. That would be nice too, and maybe that's a better way to do it. But yeah, I'd like to hear your opinions about it.
I'm sorry. I don't know much about 2D spectroscopy, but on one of your slides you had a graph showing amplitude and a graph next showing lifetimes. And on the first ones, I noticed the lifetimes were off diagonal. What does that mean or imply for the system? Or I don't even know if it's important for a lifetime one if it's off diagonal.
Yeah, so the off diagonal components are telling us. So here's an example. Yeah, so the diagonal. So this is basically telling us that the amplitude of these higher energy states. So this positive signal here refers to a reduction, and so on the diagonal, you can think of this as telling you about the population of various states. The cross peaks here, in this case, are telling us about energy transfer. So, so this is a growth here that's telling us that, you know, this feature wasn't there previously, but now it's growing in, and that's due to having excited at this frequency here. I now detect at this frequency here because of energy transfer or, you know, or charge transfer. But there's been spectral evolution in the system where previously I could excite here, and now I detect here. Yeah. I think that I'm not sure that that's true. There's always some component of diagonal. Let's see here. Yeah. So.
We have one online question. I'll do my best to reproduce this. It's from Xiaomao, Ximao, and the question is: since you are measuring events on a time scale of greater than 100 femtoseconds for event PS, I'm not quite sure what that means. Why do you need to use high resolution of 0.02 femtoseconds?
I see. So the idea there is, so actually I should be careful here. We don't have time resolution. Our measurements can't measure things as fast as 0.02 femtoseconds. But what we do need to we do need to know our time delays. So the position of the center of our peaks of our you know, yeah, the sort of time zero of our laser pulses. We need to know that extremely well because we're going to Fourier transform that time delay to get a frequency. And when you're measuring frequencies in the visible range and you want reliable frequency axes, then if you have errors larger than that, then that can give rise to artifacts in the Fourier transform. That's why.
Can you put the kinetic model back up there that you just showed a minute ago?
Yes.
There. What is it that really drives that conclusion that there are these two parallel models there, or two parallel pathways? What really is the key observation there? I've never quite been able to understand.
Right. So
why that was the conclusion that they had the charge separation between the two, the accessory chlorophyll and the
So yeah. So I think there are a number of different papers that that believe that this pathway is important. The first work was photon echo measurements by Halsworth and Prokorenko, and they did some modeling that concluded that in order to be able to explain the very rapid processes they were seeing in their photon echo experiments, that they found that if they used a model that invoked this pathway, that invoked the involvement of the chlorophyll D1, that they got better agreement than without it. So they suggested it, and then there was mid-infrared measurements by the Van Grondele group. And that actually, I should have mentioned that was some of the inspiration for doing these Raman measurements, was that they were, so they used visible pump mid-infrared probing and saw signatures that they, so infrared signatures that they attributed to charge separation at the Phaeophyton. But at the end of the day, the existence of the two pathways comes down to the analysis of the transient absorption data, whether it be with an infrared mid-IR probe or a visible probe, looking and seeing the kinetic species that seem to be spectrally distinct, that have these different time scales.
But in all cases, is it the case that you're pumping into this chlorophyll Z molecule, because you've got this slow step, this 25 picosecond step that starts out, and that's obviously going to complicate the
So here, I should clarify this. So this is how they draw their model, but what they're meaning is that the usual way to excite the reaction center is through these peripheral chlorophyll that are closer to the antenna complexes. And so if you excite the antenna complexes, then you will have this slower transfer before the charge separation. If, however, you're looking just at the isolated reaction center, then you're going to see these fast processes. So you don't have to wait. We're not just exciting the
so you don't really have selective excitation. No. That's one of the problems.
That is one of the big problems, exactly.
Congestion. Yeah. And that's one of the things we hope that a marina will fix. Yeah. What about doing mutants, say chlorophyll Z's? Has anybody done that to try to get rid of those? Because that seems to me to be the biggest complicating factor.
So there are some preparations that'll get rid of the chlorophyll Z's. But there have been some, a host of really nice mutant experiments that we would love to get our hands on some of the mutants. In particular, mutating, changing the chlorophyll or the Phaeophyton D1, for example, would I think be a lot nicer than doing the chemical reduction that we've done. We did that because it was the easiest thing to do. But other issues are whether you do a mutant or chemically reduce it, you do modify the electronic structure of the system, and so it's not as clean you can't do as clean a comparison as you'd like to do, but that's the nature of the system, I guess. But yeah, there certainly have been a number of mutation studies that have either mutated residues around the various pigments involved, or changed out some of the pigments.
And one of the things that we kind of think about is that PS2 is structurally similar to the bacterial reaction center, and this whole left-hand pathway, as far as we know, doesn't exist at all in the bacteria. Is that right, Dewey and Chris? There really isn't anything analogous to that in the bacteria.
But I'm looking at this sort of like that there are two different schemes of schemes of initial electron transfer. There's the electron transfer to the side of the right.
Yes.
Right side, not the left side. So it's not like reaction.
Right.
But the key difference is where the cation is located. The cation is located on the
Yeah.
accessory chlorophyll versus the special.
Right. Yeah. It's what does the initial electron donating.
Oh,
Okay.
yeah.
I see.
Yeah, we're not talking
Okay.
that way. Yeah.
Yes.
Right.
Okay. Mm-hmm.
Right. So you still have unidirectional electron flow, but the question is, what's the initial charge?
Yeah. Which is
state?
the initial electron donor? Yeah. Okay. I should clarify the language.
But you don't have any analog to having the cation on the accessory bacteria chlorophyll in that. Do you? It's been proposed? It's been proposed and retracted. Yeah.
And in that case, what's the strongest evidence for it?
Well, the obvious initial thing is when the reference to the initial, before you see any leaching of the special here, you see leaching of the accessory bacteria chlorophyll, and the apply indicating that they're implicated in something before you see the effect of the special.
And that's not just exciton coupling between excited states, or
that's
part of the argument. Yeah.
Right, but you have the better. Yeah. So you, I see. Okay. But yeah, you have the.
But you're really exciting all
unfortunately,
of them.
we excite everything because it's all in the same band. Yeah, that's the problem.
Yeah, the spectral congestion is really at the heart of most of the problems, I think.
Yeah.
Isn't that true?
Yeah, this is absolutely. This is the problem, and because of that, different groups, even with similar measurements, have different models for what's happening.
All right, any other questions? A good discussion. Okay, let's thank Jennifer again for a really interesting, exciting talk.